Okay, let me start here today talking about a formula, vector formula, parameterization formula, whatever. We'll use it as a parameterization tool here. So we've got a line segment that starts at one point and ends at another point. Yeah, previously in the chapter on lines we talked about a couple of chapters ago, there's a vector formula that we can use to help us do this. It turns out if we let R0 be the vector x0, y0, and then R1, let that be the vector x1, y1, it turns out then we can write a formula for a vector between the two, call it R of t, and R of t turns out to be 1 minus t times the R0 vector, and then plus t times the R1 vector. The result of that gives us, and t goes between 0 and 1. Turns out that will give us a vector, and then we can use that to parameterize it. On in. All right, so what we're trying to find here next here is the line segment from negative 5, 3 to 0, 2. And what I want to know here is I want a parameterization for that. And in other words, x equals some function of t, y equals some function of t. I want to find that line segment in terms of two functions. And it turns out if we use this formula from a previous chapter, this here, that'll do it. And let's see. So in this case, our parameterization vector here would be 1 minus t times, and again, the R0 is just the vector x0, y0, so our R0 is just going to be negative 5, 3, plus then t times R1 is just the vector with that as our endpoint, if you will. All right, and so what that amounts to is, yeah, if we complete the calculations here, of course this will be times both of those, so it'll be negative 5 plus 5t, comma, 3 minus 3t, plus t times both of those. If we add those two together, what do we got? Well, negative 5 plus 5t plus 0, just negative 5 plus 5t. And then 3 minus 3t plus 2t would be 3 minus t, wouldn't it? Okay, and so, and that goes from, turns out from 0 to 1 in terms of t. And so our parameterization would be x equals this, negative 5 plus 5t. And then the y equals that, 3 minus 3t, from 0 to 1. This would give us that line segment from negative 5, 3 to 0, 2. And if you'll note there, If we plug in x to be 0, which would be our starting point, notice it would be negative 5, 3. We plug in t equals 0. And then if we do t equals 1, we'll have negative 5 plus 5, which would be 0. And plug in 1 there, you get 2. So sure enough, that goes from negative 5, 3 to 0, 2. All right. So you just have to remember that little formula right there. That'll get you parameterization, which for our line integrals might be important, right? We use those sometimes. So let's do one here. Evaluate the line integral here over curve C for x cubed ds, where C is the line segment from negative 2, negative 1 to 1, 2. Okay, so as we recall, our line integral is just a reminder here, if we have f of xy ds, that's going to be equal to a to b f of x of t y of t, right? Times the square root of the derivatives squared added together dt. So we need to parameterize all this stuff. And so that's where, since we don't have it where we can parameterize it already, that's where that formula will come in handy. So let's first parameterize our line segment. So that's r of t equal, it's 1 minus t r0 plus t r1, where in this case r0 is just negative 2, negative 1, and r1 is just 1, 2, that vector. Okay, and so I like to go ahead and write it out. That would be negative 2 plus 2t, comma, negative 1 plus t, plus 1t, 2t. And so that gives us negative 2 plus 3t, and negative 1 plus 3t. We add the components there together. And so that's going to be our x of t, and that's going to be our y of t, and these are always, if we do this, from 0 to 1 for t. All right, so going back to our line integral then. In this case, we've got 4x cubed ds. That's going to equal the integral from a to b. Well, we've got our parameter now, 0 to 1. F of x of t, y of t, what would that be? Well, we're going to plug in, like we said, x of t is negative 2 plus 2t, which plug it in there for the x. We don't need the y in this part anyway. Negative 2 plus 3t cubed times, run into my problem here. Okay. Yeah. Yes. So we need the derivative of x with respect to t, so that would just be 3, and square that. Then we need the derivative with respect to t of y, so that would be also 3. So square root of 18 dt, which, let's see, that would be the square root of 18, which is, what, 3 square root of 2. All right, so I've got 12 square root of 2. And really it's just a little u substitution, right? U equals negative 2 plus 3t. So du would be 3 dt, du over 3 for dt. That's going to give us 1/3. U to the thirds, which is just 1/4. U to the fourth, so it'll be 1/4 negative 2 plus 3t to the fourth. And we're evaluating that from 0 to 1. Hey, look at that. 12s would cancel out, so just have square root of 2, plug in the 1, be 1 to the fourth, right? And plug in the 0, we'll have negative 2 to the fourth. So we have 1 to the fourth minus negative 2 to the fourth, which is 1 minus 16, yeah, so that would be negative 15 square root of 2. Okay. All right. So a few steps and different things that we have to go through there, but not too bad. All right. So far, on the line integrals we've only done it in 2 dimensions. But do you think we can do it in 3 dimensions? Sure. We can evaluate over a line, a curve, in 3 dimensions. I believe the book calls it line integrals in space. Meaning we can bump this up to 3 dimensions if we so choose. All right, so we're going to suppose we've got a curve C given by x equals some function of t, y equals some function of t, z equals some function of t, and t is running from A to B. That's what we got then. It's very analogous, because then the line integral of c of our whatever function in x, y, z over the arc length, ds, differential in terms of the arc length. That'll be the integral from a to b then. Parameterize everything. So it'd be f of x of t, y of t, z of t. So we've got to write basically this function in terms of t. And so then, yes, we just do extend our square root arc length integral, yeah. Arc length part. Yep, exactly. Just add the 3rd dimension there. So it'll be the square root of dz dt squared that we add, yeah. So nothing really more, just, I guess, more parts, but very analogous. Okay, so let's do one of those. Oh, no. All right, so let's evaluate the integral x, y, z ds, where c is the helix given by x equals cosine t, y equals sine t, z equals 3t, and t here I'm going to run from 0 to 4 pi. Okay, so we've already got our parameterization, so we don't have that step in this case. So we can just go. Whoops. We can just go right to our calculation here. All right, and so our first step, 0 to 4 pi is our parameter limits. X is cosine t, y is sine t, and then z is 3t. And then underneath the square root, we need to do the derivatives, all the derivatives squared. So it'll be negative sine t squared for x. Derivative of y would be cosine t squared. And then z is derivative 3, so 3 squared t. And yeah, helix is a good one to choose because that makes, what do we got here? We got 1 plus 9, so we got the square root of 10. 0 to 4 pi. Let's do 3 square root of 10. It's our coefficient, if you will. And then t, got a t here. And then here, we've been doing a little trick calling that half sine 2t. Well, the problem is here we've got a t and a sine of 2t. And the integral for that, if you'll recall, when we have something like that, how might we do it? Because substitution is not going to help us. Yeah, integration by parts. Yeah, if we do integration by parts. Quick review of that. All right, so we let u be t, and then dv is the rest. I'm just going to leave off the coefficients here and just call it dv sine of 2t dt. And so then du is dt, and then the integral of this is v, right? So that would be 1/2 negative cosine of 2t. A little bit of substitution actually involved there. And so integration by parts, you've got uv minus v integral of v du. And so that would be t times this. So it would be negative 1/2 t cosine 2t minus the integral of v, which is negative 1/2 cosine 2t du, so that would be dt. So that works out pretty good. You have negative 1/2 t cosine 2t. Negatives cancel, be plus 1/2, and then another little u substitution. So we have another half sine, 2t. And plus c, but we're going to do it over here with limits. So here's what we got. I've got 3/2 square root of 10 times, in the integral of the t sine of 2t is that, so it's negative 1/2 t cosine 2t plus 1/4 sine of 2t, and do that from 0 to 2 pi. 4 pi. Thank you. I don't think it mattered, but yeah, it would, because I have a t. Negative 1/2 times 4 pi times the cosine of 8 pi. 1? Yeah, be 1. And then plus, okay. Yeah, the sine of 8 pi is 0. All right, and then subtract, plug in 0. Well, you have 1/2 times 0, and then 0. So it's basically 3/2 square root of 10 times negative 2 pi, which the 2's cancel, so you have negative 3 square root of 10 pi.